Hi, thanks so much. My name is Will Benton, and I do work on distributed systems and data science at Red Hat, an emerging technology group. There are a lot of people doing data science at Red Hat. My team is just one of many teams. But today I'm going to talk to you about some experiences we've had and lessons we've learned running Spark and Spark applications in containers. Specifically talking about running Spark applications in containers on Kubernetes and OpenShift. A lot of these lessons will apply to your containers more broadly, but that's where our focus has been. So we'll start with some background on containers by examining some common misconceptions about what a container is and what it does, figuring out why these misconceptions persist, and also taking a look at where they break down. Now, a really exciting theme that's been a bigger point of emphasis in the community and at recent Spark summits is the shift from running analytics as a separate workload to running analytics as a part of your applications that you're putting into production. So we'll take a quick look at the sorts of architectures that make sense for deploying analytic applications in containers. Now, some of these misconceptions people have around containers involve security and isolation, and these are some of the biggest and most dangerous misconceptions you can have. So I'll show you what to look for and discuss some simple steps you can take to make it less likely that you find yourself writing an 8,000-word post-mortem on Medium after a sleepless night. The conventional wisdom about containers is that they're a low overhead way to run applications, and this is conventional wisdom for a good reason. It's true. But there are some situations where diagnosing the performance of applications in containers can be counterintuitive or confusing. So we'll look at some of the surprising problems my team has run into and at some of the even more surprising solutions, so you have a sense of where to look when you see problems in your own code. This is a short talk. We obviously can't go deep on all of these topics, but my goal is to give you a sense for the sorts of things to look for as you go to containers and help you start thinking about the trade-offs that containers offer between flexibility, security, and performance. And I'll close with some concrete suggestions so that you can decide how to best navigate those trade-offs for your own use case. So first off, just to get a sense of where everyone is coming from here, how many people in here have built a container image before? Awesome. So a lot of people have done like a Docker build. How many people are running containers in production right now? How many people are running Spark on containers in production? Cool. So just to make sure that we're all on the same page, I find it's really interesting when you ask people to define containers, right? There are a lot of sort of things people say about containers, and you often get a fuzzy answer because there's a big constellation of capabilities that goes with this word container, and people are trying to capture every aspect of this. Some people think of containers as sort of like a lightweight virtual machine. Still other people emphasize that, oh, this is a way to run an application isolated from other things on the same host. And still other people say, oh, a container, that's just the thing I run in Docker, or that's the thing I run in Kubernetes, right? All of these have some truth to them, but they're also sort of wrong in subtle ways. So to figure out why they're wrong, let's look at what a container actually is. And we'll start by looking at just the humble Linux process. An ordinary process has an environment and some pointers to kernel resources. Some of these resources are in things called namespaces, like process tables, root file systems, and network routes. When you run in a container, you have a process table, a root file system, and a network route. But because these things are namespaced, the things you can see are going to be different from other processes running on the same host. And that's controlled by the kernel. So this is an ordinary process here that's running with a different process table, a different root file system, and different network routes than other processes on the same host. Some other processes on the system can see it, and sometimes it can tell that it's running in a container. But this is all a container really is. Containers also have some resource limitations imposed on them by the system. The only thing that your container runtime is going to do is provide a convenient interface to package up a process running in these special namespaces and optionally running with these special resource restrictions with a file system image to load as it's written. By contrast, if you run a virtual machine, you have an ordinary process that's running a whole operating system on your host. Other processes on your host can only tell that there's a virtual machine hypervisor running. They can't tell what's running in that. Processes running inside this virtual machine can't tell that they're not running with full control of a host for the most part. So we've seen that a container is different from a virtual machine, although a container does address a lot of the same use cases as virtual machines. And it is a pretty lightweight way to accomplish those things. Containers provide some isolation through the namespacing mechanism and resource limits, but they don't provide total isolation, and we'll see the ways that the isolation breaks down later in the talk. Finally, and I think most importantly, a container isn't just something you run in Docker or Kubernetes. A container is just a Linux process with some special namespace settings and optionally some resource constraints. So hopefully we have a better idea of what containers are at this point, and now we can look at how to best make use of them in our Spark applications. Let's start by taking a look at how Spark fits in to a contemporary containerized application architecture. When we're talking about applications in containers, we're talking about orchestrating multiple containers together. And the most popular and successful way to do this has been by using what we call microservice architectures, where our applications are structured as a bunch of independent components with well-defined interfaces, typically minimal sets of responsibilities and SLAs. These are easy to scale up because you can run a bunch of them on the same host if you have a really big machine to run them on. But you can scale them out as well by running them on separate hosts, since they communicate through explicit interfaces. If one of these things becomes a bottleneck, you can make a bunch of copies of it and run it behind a load balancing proxy. Because these things are stateless commodities, if one of them crashes, you can replace it, sometimes even before other parts of your application really start getting affected by it going away. So this is sort of the high-level view of application architectures for containers. Let's look at how a Spark application might fit into this. At a high level, your application is going to be federating, transforming, aggregating data from a bunch of different sources. Streams, files, structured and unstructured data. You're probably also going to be archiving your raw data so you can play it back later if your pipelines change, and probably archiving some of your transformed data too. In these figures, I'm using blue to represent data stores or data sinks and orange to represent compute components. Once we have this data, we want to learn from it. So our application is going to train models and cache those models in some sort of store so that they can be accessed by other parts of the application that are going to make predictions. We may also feed that back to our data transformation so that we can use the results of our model to transform new data that we see. We can have a great application, but it's useless if people can't interact with it. So we need to support a bunch of user interface components too. In today's applications, that means having an actual interface that end users interact with, a web application, a mobile application, some interface for developers or data scientists to tune hyperparameters or other details of the application, reporting interfaces for accountants in the business side, and a management interface for your ops team as well. So let's look at how this fits into containers. Your persistent storage is going to outlive any particular deployment of your application. So it's going to live outside of containers. But the operational storage, that cache for your models, that's something that you can run in a container and easily replace when you redeploy your application. Our user interface components are typically just web applications. So these can run in stateless containers pretty easily. The place where things get interesting is looking at the compute layer. We need something that can efficiently transform, federate, and process a lot of data from multiple sources. We also need something that's going to be resilient to failure and able to scale out elastically. Where are we going to get something like that? It's Spark, right? It's not a trick question, right? Spark was invented before the current popularity of containerized microservices. But since every Spark executor is really just a microservice that calculates the values of partitions, Spark works really well in these kinds of architectures. So if you have a multi-tenant Spark cluster that you've used in the past for analytics jobs, you may be thinking, well, I'll just have a resource manager to schedule my apps and a cluster scheduler to schedule my Spark cluster. But this doesn't work out as well as we'd like. The resource manager that's scheduling our applications has to cooperate with the cluster scheduler that's managing our Spark cluster. And there's some inefficiency there. We found that a better model is actually to embed individual Spark clusters in applications, and then everything can be scheduled by the same resource manager. And this makes a lot of sense because we're putting analytics into production as parts of applications, and our Spark clusters can grow independently as they need to with the requirements of our applications. So we've gone over the high-level view of how to organize applications, Spark applications, to run them in containers. Let's talk about security now, because a great application isn't great if it crashes or if it's exploited, right? I think the most important question for security when running in containers is, what are you comfortable with and what are your requirements? If you're running a shared resource for teams of developers from a single organization, you need to help protect these teams from each other's mistakes. If, on the other hand, your goal is to run a multi-tenant containerized Spark as a service offering and open it up to customers from the general public, you have a different set of concerns, and I hope you're not getting all of your security advice from this talk. We're going to be focusing on that former case. Since containers are ephemeral and launched from immutable images, a big class of exploits you see with shared servers or sort of persistent servers don't really apply to containers. But there are always trade-offs between performance, flexibility, and safety. So let's start by looking at where containers fit into a much broader continuum of security options. The most secure way to run a bunch of services is to run them on individual computers that aren't connected by a network. This is also the most boring and least flexible way to run a bunch of services, right? They can't talk to one another, you can't do anything interesting. Having multiple services running on multiple hosts that are networked together, you can run different services on different machines. Your whole system is going to be affected if one of these things crashes or starts misbehaving. But a crash, even of an entire machine, is not necessarily going to take out other services. And because communication between these machines is going to happen in well-defined ways, either through service interfaces or through an explicitly shared file system, you sort of have a sense of how these things are going to fit together, and you have a sense of what the surface area is for where problems can occur. We can go a little finer grained by running everything in virtual machines on the same host. We can run every process in a virtual machine on the same host. This gives us a lot of isolation. One of these guest operating systems can crash without affecting the others, without taking down the host, but we have that overhead of running everything under a hypervisor. And of course, if that host operating system crashes, it takes down all the guests. Going finer grained still, we can run everything in containers. Containers offer extremely low overhead, and namespacing and quota mechanisms give us pretty good isolation for a lot of cases. And typically, our containers won't be sharing a root file system, which eliminates a big class of problems you see with remote exploits. However, if the host crashes, again, it takes down all of these services. If we want absolutely no overhead and also absolutely no isolation, we can just run everything as a separate process in the same namespace on the same host. Please don't do this for any reason. I think that the trade-offs containers offer make a lot of sense. You get nearly no overhead with a reasonable amount of isolation, but there are still some things you can do to improve the isolation that you get. The first thing you can do is not totally trust the isolation you get from containers. If you run SE Linux, you can dramatically limit your exposure to bugs in the container runtime or to a malicious code in a container. SE Linux effectively walls off processes and files, meaning that if something escapes a container or can see outside of its namespaces, it won't have unrestricted access to the rest of your host. In fact, just within the past couple of months, people who were running SE Linux were protected from a zero-day exploit in the Docker runtime. The next thing to consider is that root in your container is the root user on your host. A containerized process that's running as root and somehow manages to change or escape its namespaces can access everything on your host as root. In general, you don't want to run code as root in containers for the same reason you don't want to run code as root on the host in ordinary processes. Now, there is a mechanism to do user namespacing, and this has been about 6 months to a year away since I've been interested in it, which has been about the last 3 years. You can enable these user namespaces as an experimental option in recent Linux kernels and Docker releases, but there are still some usability and security issues, so it may not be something you want to run in production. So namespacing provides great isolation for namespaced resources, and there are ways to use SE Linux to improve the protection we get if someone escapes a namespace. But not every resource in the kernel is namespaced. If we have a runaway process that starts creating a bunch of non-namespaced resources, then that can affect the ability of other processes to make progress. An even more interesting kind of denial of service comes from the fact that all of these things are still ultimately running on the same kernel. So if you have code that crashes the host kernel, it's going to bring down the whole system and every container running on it. Fortunately, kernel panics from user space code are pretty rare. I don't see them that often. I guess I see them more often than I'd like, but it's not that often. But this is yet another good reason to really test and thoroughly vet everything before you put it into production. The last security issue we'll look at is an especially interesting one that applies to containers even more than it applies elsewhere. And if we remember that persistent storage lives outside of containers, and that we're typically accessing this through a service interface, we're going to need credentials to get at our persistent storage. Our container images, though, are immutable, and we want to use them in a bunch of different contexts and a bunch of different configurations. We're going to use the same images for development, test, and production. So we need a way to pass these credentials to the container image so it can access them at runtime. One thing that a surprising number of people still do, please don't photograph this slide, is store their credentials in source control. This was a terrible idea 10 years ago, when having your credentials for your web application exploited meant that someone could get access to the database for your CMS on a shared server. It's an even worse idea now, when these credentials mean that someone could get access to a whole lot of sensitive data for your organization or your customers, and also potentially rack up a huge bill at your public cloud provider. We don't want our credentials to be exposed to anyone who can see our source control. A slightly better idea is to put credentials in the container's environment. This requires a little extra configuration and setup, but it doesn't have the problems of putting things in source control, and it lets us change which credentials we use to access things in different configurations. However, your environment could become visible to other processes running on the same host, and other users who can launch containers on the same host may be able to see that configuration. So it may not be the best option, but it's a more reasonable option. The best thing to do is really to use a dedicated mechanism for storing secrets and making them available to containerized applications. That might be something provided by a container management system like Kubernetes, or by a separate service that's designed for the purpose of handling secrets. Using one of these services gives you both flexibility and security. So this is really the way to go as fast as you want. So we've just seen how to navigate some of those trade-offs around security. A lot of times security trade-offs have obvious performance implications as well, and containers have their own performance trade-offs and surprising pitfalls as well. So we're going to look at some of those next. Now maybe you just heard me talk about security and you said, oh, well, I like the idea of running everything in containers. I like that developer workflow, but I'm just going to put my containers in VMs so that they're actually isolated from the rest of the machine. Well, you could do this, but you don't have to. And this will hurt your performance, and we've seen that you can get really good isolation by using lighter weight mechanisms like SE Linux, using non-root users, using ephemeral user IDs. Another thing that a lot of people worry about is this virtual network routes that you have in containers, and especially for data-intensive applications like Spark. Well, my team has actually looked at this, and on the applications we've run in production as well as on synthetic benchmarks, I have a colleague who's looked at this a bit lately, and we really actually see that this extra network routing is no big deal. We've seen less than a 5% impact on training machine learning models typically from this virtualized networking. One thing related to I/O that you do have to worry about, though, is how you've configured storage if you're using Docker or Kubernetes. There are a lot of articles you can read on this online, but if you use a loopback device, expect your performance to be really bad for disk writes. Another surprising issue with containers is interaction between your resource quotas and some common optimizations that you might want to use in your application. For example, your typical configuration for the JVM may be to use the parallel garbage collector. The parallel garbage collector picks a number of threads to use based on how many cores the JVM sees available. Now, a colleague of mine at Red Hat has shown that if you have a small number of threads, the serial garbage collector is actually going to be better, especially if you're running in one of these resource-constrained environments. If you have a small number of threads, the amount of communication to coordinate the work of garbage collection is not going to get you any benefit in extra parallelism. And the serial garbage collector will actually use less of your CPU quota and get more work done. Another really surprising place where you see this is in Spark's clever use of operating system buffer cache. When you have a Spark shuffle, Spark essentially treats your disk as an off-heap memory area that it can write to and that isn't necessarily going to hit the disk, right? If you write and don't sync, then that data stays in your operating system cache. It only gets written out if you run out of physical memory on the machine, and in most cases, it never actually hits the disk. So Spark is sort of cleverly using this to get extra memory and caching for free. However, if you're running in a severely resource-constrained environment on a container, that buffer cache use counts against your memory quota. So that's another thing to keep in mind. Similarly, with memory, the JDK is not necessarily going to be able to see how much memory your quota allows. It will see how much memory is in the whole machine. So if you set your heap sizes in conjunction with your resource quotas, you're less likely to have a JVM asking for more memory than your kernel is willing to allow it to use. The JVM community is actually looking at becoming a better citizen in containers, and OpenJDK 9 will actually have a fix for this issue. So it is something on the community roadmap there. So I'm really excited about containers. I like developing applications in containers, and since most of the applications I like to develop involve Spark, I'm really glad that Spark works well in containers. I like the developer workflow. I like the infrastructure efficiency. I like the fact that you can write something once and port it between, your laptop, a public cloud, a private cloud, different cloud providers. There are trade-offs to containers, like with anything else, but I hope they make more sense to you now than they did 20 minutes ago. Here's some of what we've learned. Spark works really well in containerized microservices architectures because Spark executors are microservices. A really nice thing about how easy it is to spin up a Spark cluster is that you can have a Spark cluster for every application that's just dedicated to that application. And you can manage multi-tenancy at the container orchestration level. Persistent storage, which we're defining as something that outlives your application, is going to live outside of your containers. And it's probably best to access that through service interfaces like object stores or databases so that you can be flexible to change where you actually store that data ultimately. On the security front, a lot of common sense things that apply to running regular processes also apply to running regular processes in namespaces or containers. It's not safe to run arbitrary code just because you put it in a container. It's not safe to run services as root just because you put them in a container. Even if you do everything right, you should still run something like SE Linux to minimize your exposure to error and malicious code. And if you have to manage credentials or other secrets, don't invent your own system. Use something that other people use and test and will work well. On the performance front, you don't need to run your containers in virtual machines to get isolation. You can get great isolation from using SE Linux, and you avoid the performance hit that way. I really encourage you to measure everything and not let your assumptions about what worked in one container deployment, or what worked in bare metal, or what worked in another Spark environment, color how you configure your applications for containers, because things will be different. And things that are big performance wins in one environment are going to be minor performance losses in others. And in particular, the interaction between the JVM and resource quotas is something to pay close attention to. Just a couple of bonus configuration takeaways. Typically in containers, you have a stream of logs going to standard out or standard error. You may want to install a custom log formatter so that your stack traces appear on a single line, and they'll be easier to search and collate later. I recommend using non-root users. You can even take this a step further and use random user IDs, but then you have to do some extra configuration to make sure that the Hadoop libraries won't get confused. At this time, I'd like to thank you for coming to this talk and point out a couple ways you can get in touch if you have sort of longer questions about this. I answer email, and I'm not a regular tweeter, but I answer tweets. And this website here, radanalytics.io, is some tooling my team has built for making it easier to deploy Spark and Spark applications in containers. And the link on the bottom is my personal blog, where I occasionally post articles, usually about Spark or about distributed systems. So at this time, we have a couple minutes for questions, and I'm happy to take any ones you have.
A quick question on persistent storage. So we have a sort of a problem here because we want our container to be, you can basically stateless. So you don't want any storage attached to it. What's your vision on this? Do you want the persistent storage to be something like a Hadoop all connected through HTTP? Or do you view storage to be attached? How do you view the storage situation with containers? Because Spark does require a lot of storage.
That is a great question, and I have 3.5 minutes for all the questions, so I can't give you an exhaustive answer. But I think that the important things to keep in mind with storage in containers are, yeah, your persistent storage is going to live outside of the containers. There are ways in Kubernetes to say, I'm going to set that up as a file system mount. There are ways to say, I can access an S3 endpoint via Hadoop AWS. And I think that really an object store interface or a database is the way to do persistent storage for containers. And we've found that if you're running an object store sort of in the same rack or in the same data center as your Spark applications, it's not a big performance hit, actually.
We have time for one more question. All right.
So on the performance takeaways, you mentioned that you wanted to avoid hypervisor overhead. But if you were to deploy your containers to the cloud, the servers you get are pretty much virtual machines on hypervisors. So how do you address that issue? Thank you.
Yeah, so in that case, with a public cloud provider, you pretty much have what they give you. Right, and you don't have the option to say I'm going to change my infrastructure at that point. But if you're running locally, and you're running for a single organization and you have a private Kubernetes installation, there's no reason to layer that on top of virtual machines as well.
All right, let's give a big hand to Will Benton. Thank you, Will. We'll be at the back of the room. If you have more questions, feel free to chat with them. Thank you.